Sir, good afternoon. Hello.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir. So,
Can see me?
are we-
Yeah, sir. Good afternoon. Yeah, I was
Good
mute.
afternoon.
Yeah, yes.
Such a pleasure meeting you, sir, here online.
Yeah.
Wish
My
it
pleasure
was
too, sir.
physical.
Yeah. Okay. And especially somebody from the armed forces background, it's always a pleasure to meet
Thank you so
because
much, sir.
yes, I was very working very closely with the Indian Navy. Yes,
That's right.
great.
So, at MIT Manipal, so we are preparing ourselves for the orientation, which is going to start from Monday onwards.
Okay.
Yeah, so big batch of students. Will have at least 4 batches. I
Yeah.
I think some of the students were present for this
Okay.
kind of inauguration.
Okay. Yeah.
Kamath sir, are you there?
Yes, sir. I'm there. Sir.
So after my speech, sir, I'll have to go and attend the other meeting. We have a Team 5 meeting.
Yes, sir. Yes.
I think it also
Yeah.
starts at 3:30, but I told them I'll join them late. So you'll have to excuse me after this, sir.
Okay, sir.
So can we start?
Shilpa, can we start?
Yeah, sure, sir.
Good afternoon. Respected Director, sir, honorable dignitaries, HODs of the departments, faculty members, colleagues, and my dear students, a very good afternoon. Today we have gathered here for the inaugural ceremony of the IEEE Geoscience and Remote Sensing Society student chapter under IEEE-SB at MIT. I'm Dr. Pooja Nag, Assistant Professor from the Department of Mechatronics, and I thank you all for joining us in this inaugural function. So let us begin the inaugural ceremony by seeking God's blessings with an invocation song by Dr. Shilpa Suresh, Assistant Professor, Department of Mechatronics.
Thank you, Pooja ma'am. या कुन्तीं तुषारहार धवला या शुभ्रवस्त्रावृत या वीणा वरतण्डमण्डितकरा या श्वेत पद्मासना या ब्रह्माच्युत शङ्कर प्रभृतिभिर्देवैः सदा पूजिता सा मा पातु सरस्वती भगवती निशेषजाड्यापहा.
I now request Professor D.V. Kamath, HOD, Department of Mechatronics, to welcome the gathering.
Very good afternoon to you all, sir. Hearty greetings to you all. IEEE student branch at MIT Manipal is a highly active branch with multiple activities being carried out in the form of workshops, webinars, competitions, and hackathons by our very enthusiastic students and able faculty members. MIT also has a large number of faculty members who are professional members and senior members of IEEE. IEEE student branch at Manipal has various student chapter societies. IEEE Engineering in Medicine and Biology Society, Circuits and Systems Society, Communication Society, Signal Processing, Computer Society, and Robotics and Automation Society. So IEEE Geoscience and Remote Sensing Society is the latest addition to this series. The Geoscience and Remote Sensing Society is a community of researchers and practitioners involved in collaboration and design development of tools to understand our interaction with Earth's ecosystems, to monitor its environments, and to characterize potential risks. For aspiring researchers and the community, helps to share their ideas, methods, data sets, and to stay informed about the recent developments and the job opportunities in this field. There are several IEEE members, researchers who are inclined to work in the areas of remotely sensed data analysis and geographical information science for various applications. And IEEE GRSS student branch chapter at MIT is the second one formed under IEEE Bangalore Section, first one being at NITK Surathkal. The chapter primarily aims to improve the quality of such research by effective collaborations with the international level and national level research institutes. Currently, we have a small number of BTech student members of this society from different departments like Mechatronics, Electronics and Communication, Computer Science, Information Technology, and we have one PhD scholar from Mechatronics department. So I feel we must extend this student membership drive to other MTech students as well, to other departments like civil department, data science, and so on. Here, I'm reminded of a popular quote from a world-renowned Chinese philosopher Lao Tzu: "The journey of 1,000 miles begins with one step." Today, the student members of IEEE Geoscience and Remote Sensing Society student chapter at MIT are beginning their journey with their first step, and we all have joined virtually to participate in this inaugural function. On behalf of the Department of Mechatronics, MIT Manipal, and IEEE Student Branch Manipal, I wholeheartedly welcome Mr. Jayaram Kolangara, scientist, former Deputy Director, Directorate of Special Projects, ISRO, the chief guest of this momentous function. I also welcome the guest of honor, Dr. Jaya Sreevalsan Nair, Chair, IEEE GRSS Bangalore Section. It's my immense pleasure to welcome our beloved Director, MIT, Dr. Anil Rana, the guest of honor of today's function. I welcome our beloved Joint Director, MIT Manipal. I also welcome administrative heads of MIT, associate directors, HODs, various IEEE office bearers, and academic community, the faculty members, research scholars, MTech and BTech students of different departments, all the professional IEEE members, and all the IEEE student members of various societies like Robotic Automation Society, GRSS, engineers from industries. I welcome one and all. Over to Poojanak.
Thank you, sir. Today, we are honored to have our director, sir, Commander Dr. Anil Rana, in this inaugural function. And I request Moogala Smrithika, Student Chair, IEEE GRSS Student Chapter, to introduce our guest of honor. Over to you, Moogala.
Good afternoon to one and all. I take immense pride in introducing the person who is a source of guidance and inspiration to all the students of MIT. He has served as a commander in the engineering branch of the Indian Navy in various roles and has over 30 years of experience in the industry and academics. He has a PhD in reliability engineering from IIT Mumbai and MTech from IIT Delhi. Post his naval service, he served as Associate Dean in Research, Professor in Mechanical Engineering in Fiji National University in Fiji Islands for 5 years, followed by Dean and Professor in Symbiosis Skills and Open University, Pune. He was the Dean, Faculty of Manufacturing Skills and Dean in Academics in BSDU Jaipur before taking over as Vice Chancellor of Oriental University, Indore in February 2021. His research interests lie in the field of reliability engineering, maintenance engineering management, stochastic Petri nets, machine learning, fuzzy and non-neurofuzzy applications in the field of maintenance engineering, etc. He has a long list of publications in international and national journals that includes various book chapters in Springer publications. I now request one of our guests of honor, Commander Dr. Anil Rana, the Director of MIT Manipal, to enlighten us with a few words. Thank you.
Thank you so much. The chief guest of today, Mr. Jayaram, who's the Scientist G and a former Deputy Director, Director of Special Projects in ISRO headquarters. Guest of honor, Dr. Jaya Nair, Chair IEEE GRSS Bangalore Section, and is also Associate Professor CAC IIITB. HOD, Dr. Kamath, faculty members who are present here today, and my dear students. It gives me immense pleasure to be a part of this inaugural function of IEEE GRSS at MIT. When it comes to geoscience and the application of remote sensing in geoscience, we all are very aware as to what are the application, whether it is mineral water exploration, hydrocarbon exploration, talking about identification of sedimentary rocks, environmental conditions, etc., etc. There are other applications also, but when I come from defense, to me, remote sensing can provide so many applications in both general as well as covert operations of the military. And with coming with the satellite communication era, especially for the defense satellites, we know it has provided us the much needed security of our communications. But not deviating from the topic, IEEE student body, I think, has done a very right thing of coming up with this GRSS IEEE student chapter. This would provide a platform for the students to learn a lot from the experience of the experts who are there in this particular field, and also will provide them it will provide them an opportunity for both knowledge development as well as knowledge dissemination. I am sure our clubs, which are very active in all the areas at MIT, whether technical, cultural, would find this particular student chapter to be very useful, and they will take it forward to come out, do research, work with different projects. From MIT itself, I remember last year when we were interacting with the DC's office, there was a requirement that they had projected to us about working on disaster management area. And we are already formed a team. We are working on that. There are some requirements of data that was needed by our geoscience department. Professor Balakrishna K, I think he's spearheading that particular project. And very soon we would have a system which will present to the DC's office that will take care of, when we talk of disaster management, at least the flooding disaster, which happens very routinely during the monsoon season in this particular area. So without much ado, I think I'd like to move forward and let the workshop or let the inaugural function go ahead. I would like to wish the IEEE GRSS student members and faculty advisors a grand success. And I hope that this particular student chapter will do a lot good to the students in knowledge dissemination in this particular area. And I'm sure that they will do work on a lot of projects and come out with a good number of publications too. Thank you so much. You'll have to excuse me because I have to attend another meeting. So half my mind is over there. I'll like to leave here now, and all the best to all of you for the inauguration function too. Thank you so much.
So thank you, sir, for the very encouraging words. It is our great privilege to have Dr. Jaya S. Nair, Chair, IEEE GRSS Bangalore Section with us today. And I request Deeksha Sabari, Joint Secretary, IEEE GRSS Student Chapter, to introduce our guest of honor.
Dr. Jaya Sreevalsan Nair is currently a faculty member at the International Institute of Information Technology, Bangalore. She leads the Graphics Visualization Computing Lab and is one of the core team members of the eHealth Research Center at IIITB. She has obtained her PhD in Computer Science from the University of California, Davis, after a BTech from IIT Madras and an MS from Mississippi State University. She has research interests in data visualization, scientific computing, computer graphics, and computational topology. She works on modeling data for effective visualizations and identifying appropriate visualizations for complex data sets. Her work has been supported by grants from SERB, Department of Science and Technology, the Government of Karnataka, Intel, and IBM, to name a few. Prior to joining IIITB, she had worked as a scientific programmer at Enthought Incorporated Austin and as a research associate at Texas Advanced Computing Center, the University of Texas at Austin. She is also an ACM member and IEEE senior member and the chair of the IEEE GSS Bangalore Section slate. I'd like to welcome Dr. Jaya to share her remarks with us.
Thank you, Deeksha. I think I'll just say a long string of thank yous here. So thank you, Dr. Pooja Nag, Dr. Shilpa Suresh, and a very thank you to Professors Kamath and Anil Rana, Commander Anil Rana, for extending a warm welcome to everybody present here. And it's a pleasure to have Mr. Jayaram as a chief guest as well. So I am representing IEEE-GRSS Bangalore section here. So I'll just briefly mention about what it is about and how the student chapter that is getting inaugurated here today will be an integral part of the chapter itself. Right. So the IEEE GRSS has been previously mentioned all about how geoscience and remote sensing is very important in terms of technology growth for the country. And it is highly multidisciplinary. So as Professor Kamath rightly mentioned, like students from several departments are already on it is a good sign of that. So IEEE GRSS Bangalore section started in started in 2012 by Professor Jaya of Indian Statistical Institute, Bangalore, and he was the founding chair then. The current slate that we have that I'm chairing has Dr. Shyamlal from NITK as the vice chair, Dr. Nagajyoti Kannan from ISRO as the treasurer, and Mr. Gurudatta from MapMy India as the secretary. So we took over in 2021 during the pandemic. So we had the opportunity to sort of exploit the virtual event organization, and we sort of kickstarted a whole bunch of events as a part of the GRSS chapter. Now, Dr. Shyamlal is highly instrumental in starting all the student chapters, starting with the NITK one and this one. He is the wizard behind making all of this happen. So the idea is we already have a bunch of student events, and our job now is to sort of transfer the responsibility of holding mapathons, hackathons, poster presentations, all of that, where students are going to showcase their work to the student chapters to manage and conduct. And at the same time, the students can also capitalize on and exploit the other events and strategies that we have at the chapter in terms of networking and expanding their own knowledge in geoscience and remote sensing through a bunch of public talks, the GRSS Distinguished Lecture Series, which has international speakers, etc. So I already see a lot of good things that is going to come out of this chapter, given the support that the chapter has in-house. And I wish the chapter great success and all the very best for this inaugural session. Thank you very much. Happy to be here.
Thank you, ma'am, for briefing us about the IEEE Geosciences and Remote Sensing Society activities. It is our great privilege to have Mr. Jayaram Kolangara, former Deputy Director, Directorate of Special Projects, ISRO, with us today. And I request Babita, Treasurer, IEEE GRSS Student Chapter, to introduce our chief guest for the inaugural address.
Good afternoon, everyone. I feel extremely honored to introduce today's chief guest, Mr. Kolangara Jayaram, former Deputy Director, Directorate of Special Projects, ISRO Headquarters. Mr. Kolangara Jayaram is a graduate in Electronics and Telecommunication Engineering and MBA in International Business. He served as Satellite Communication Engineering Specialist with diverse experience spanning 40 years. He served the Indian Space Research Organization with distinction from 1982 to 2018, having joined as scientist or engineer and remitting office as scientist grade G and deputy director at Directorate of Special Projects, ISRO headquarters. He was instrumental in conceptualizing, realizing, and operationalizing many critical SATCOM, ground and space systems, networks, and associated infrastructure with Indian National Satellite System, Indian Remote Sensing Constellation. He is the recipient of ISRO Team Excellence Award for Innovative SATCOM Broadband Data Transport System Design. He has represented ISRO in various scientific forums, national and international seminars and conferences. He is currently serving as the advisor at Bharat Electronics Limited and has been passionately involved in spreading space science and technology awareness amidst students. We are grateful to have with us Mr. Kolangara Jayaram as our chief guest and keynote speaker for today's event. On behalf of IEEE GRSS Student Branch Chapter MIT, I invite you for the inaugural address. Sir, please take over.
Thank you, and thanks again for the great welcome. Dignitaries on and off the dais, students, other invitees, and other members in the today's gathering. Very warm good afternoon to all of you. And I am extremely happy and privileged to be amidst you all today when the student chapter of IEEE GRSS comes into existence at MIT. And I'm also very delighted to know that this is the second chapter coming under the aegis of IEEE GRSS Society of Bangalore. And just I was listening to Dr. Jaya, who was telling that a lot of activities and proactive R&D and a lot of activities happening in the Bangalore chapter. And it is my wish and hope that this new chapter that is getting inaugurated today will seamlessly enjoin that Bangalore chapter and start working in with all sort of means dedication and take up all the challenges. I take this opportunity also to congratulate all the people who are behind this important step that intends to promote and improve the quality of research in the emerging yet crucial domain of remote sensing applications. And I also hope that this particular center would grow into some sort of a focal point for technical activities around remote sensing happening in and around Manipal and this part of the country. We are all aware that space of late has emerged as the technological high ground, and space-based systems and applications impacts every aspect of the 21st century life on Mother Earth. Business, governance, security, safety, education, manufacturing, navigation, treaty compliances, financial transactions, healthcare, you name any facet of modern life, space systems are there. And you can also note that the space economy is worth billions of dollars globally. It's emerging as the real, the prime mover for economic growth all across the globe. So space-based remote sensing also plays a major and critical role. And space-based remote sensing enabled applications and services nationally and globally are actually driving the life. You can see the influence and impact and dependency on these remote sensing services in the economic progress across the globe. Change detection is one of the most important activity enabled by the remote sensing. You look at the energy sector, engineering and construction, land coverage, natural disaster detection, forewarning, mitigation, natural resource management, environment monitoring, defense and security, all sectors depend on remote sensing applications. We can proudly state that our country has made remarkable progress in all domains of space-based remote sensing and leads globally, probably the application scenario in the peaceful application of space. GIS and other emerging technologies, coupled with the artificial intelligence and virtual reality, etc., including machine learning, have opened up great opportunities. While the space systems are growing and are being built and launched, the question of the voluminous data that emerges out of this multiplicity of sensors of all types and all makes, a lot of data is coming down from space and it's getting archived. And it is a very sorry state of affair that this data goes unutilized to a great extent. So it is high time now to go out of that boxed mentality sort of thing, using technology, this data for the conventional governmental applications, and more and more researchers and students, engineers, scientists, all should uh, uh, get into this possibility of accessing the data and doing a lot of analysis and product generation. And with the opening up of the space sector for public, with the recent brave policies of the government, I think this is going to be a path-breaking avenue for every one of us. So with this background, I hope and wish that this chapter of IEEE GRSS will emerge as the technology high ground and promote and indulge in advanced studies and research in the RS-enabled geographical information system and geosciences front. And I wish the chapter all the best. And for formality's sake, I formally declare this chapter of IEEE GRSS at MIT open. Thank you, one and all. Jai Hind.
Thank you, sir, for inaugurating the student branch chapter. I'll now introduce the IEEE GRSS Execom members. So we have Dr. Shilpa Suresh as the faculty advisor. Smrithika Moogala is the student chair. Srijit Radhakrishnan as the vice chair. Samarth Shankar, the general secretary. And joint secretaries Deeksha, Sabari, Nikhil Mohan, and Babita as the treasurer. Now, I request all the attendees to kindly switch on your camera for a photograph. All attendees, I kindly request to switch on the camera. Okay, thank you so much. Now, with much honor, I invite Mr. Jayaram Kolangara to grace the occasion by presenting a talk on space-based remote sensing and Indian perspective. Over to you, sir.
Thank you. So I will go to presentation mode.
Sir, you can share your screen.
Yeah, I'm doing that.
Yes. Okay. Yes, sir, we can see that.
Can see now?
Yes, yes, we can see.
Can we start?
Yeah, sure, sir. Sure.
Yes, sir.
You're able to listen to me, no?
Yes, sir, we
Yeah.
can.
Okay. Good afternoon. And at the outset, I once again thank the organizers, especially Dr. Shilpa Suresh, for extending an invitation to me to be amidst you all today and to deliver the keynote address, which I must, in all honesty, admit something I'm not used to. Anyway, now let me take an advance bail as well. By any stretch of imagination, please do not consider me a remote sensing specialist. I do not fancy myself to be one either. I'm basically a satellite communication systems engineer. Having said that, during the last part of my stay with ISRO, over a span of almost 12 years, I was privileged to be part and contribute to the efforts of a dedicated team of technologists trying to plan, build, and operationalize space-based systems and applications focused on national safety and security. What we would call responsive space, a space that would respond to emerging needs of the country with a focus on the safety and security. The task was to conceive the user requirements for space systems enable command, control, communication, computers, intelligence, surveillance operations, and to conceive responsive systems, many of which have since been commissioned and operational. So what I have learned then is what I will try to share with you today. A primer of sorts on the rudimentary remote sensing principles and applications, evolution of the remote sensing in the Indian context, relevance in the current context globally, and finally, if time permits, the global scenario and emerging trends. So let us move on. Let us look at the basic definition of what remote sensing is. The science of remote sensing is essentially sensing from a distance. Remote is away from or at a distance, and sensing means detecting a property or characteristic. This remote sensing has been very much there as part of our day-to-day life, where humans and many other types of animals accomplish this task with the aid of eyes or by the sense of smell or hearing. So remote sensing is not new to us. Only maybe the space-based remote sensing is the new domain that we will have to explore. There are umpteen number of definitions for remote sensing. At least I know I have come across at least 10 of them. But in the current context of space-based remote sensing, the most apt definition would be, it is the science and art. I underscore that statement, the science and art of obtaining information about an object, area, or phenomenon through the analysis of data acquired by a device, space-based device in this case, the sensor in this case, that is not in direct contact with the area, object, or phenomenon under investigation. So here the context and the importance is given to the science and art part. Why art part means we'll come across in the part of the further presentations. Object, area, or phenomenon are the three important aspects that we would like to see from space. This is the definition that we should keep in mind. So remote sensing, let's forget about the definition part. Actually, essential things of remote sensing is there are three elements involved. There is an object to be sensed, or a place to be sensed, or a phenomenon to be observed. And there is a sensor, and in between there is the medium or electromagnetic radiation. So three elements are the basic rudimentary requirements for remote sensing. The science of remote sensing has emerged as one of the most fascinating subjects over the past 3 decades. Earth observation from space through various remote sensing instruments have provided a vantage means of monitoring, land surface dynamics, natural resource management, and the overall state of the environment itself. Coming to the concepts of remote sensing or the components of remote sensing, as we can see, there are 7 elements A to G here involved. So this is basically extension of that 3-point charter that we said there. There is a source, there is a body to be sensed, there is a sensor, and in between there is the media. Slightly elaborating on that, we have the energy source or illumination A, the radiation and the atmosphere B, interaction with the target C, recording of the energy by the sensor. These 3 belong to the body being sensed and the atmosphere or the media in between. This is sensor part, recording of energy by the sensor. Subsequently, the space-based sensor has to transmit the sensed data or information through any media or a communication link or a data link, the transmission, reception, and processing part. Subsequently, this data has to be analyzed, interpreted, and some sort of data product generated. And finally, it transforms into the application. So it is in this area that lot of activity needs to be done, because it is here on ground. Actually, always we would like to have the complexity of operational system back on ground rather than in the space, because if you build the complexity of some onboard signal processing or onboard computation, etc., first of all, the systems becomes very complex, and in case of any contingencies, the mission is lost. So generally, when we decide, especially in ISRO and everywhere across the globe, when we do a space system design, we, to the extent possible, the signal processing and the complexities involved, we try to bring it down at the earth, where we have got much handle on these things in terms of technology, in terms of equipment, in terms of redundancies, etc. So it is in this area, interpretation and analysis and the applications that would extract the data or something else out of the voluminous data that we have. Because some sensors that we employ, actually it will give multiple services, or the data can be duplicated in many modes than intended. Now let us look at the remote sensing measurement elements actually. So we have got remote sensing platforms, either as an orbital platform. When you talk about orbital platform, it could be the low Earth orbiting domain, the LEO, what we call low Earth orbiting platform domain, which essentially commences somewhere from the 500 kilometers to around 2000 kilometers. All those remote sensing satellites fly around in this area, because this is the area from where, with their optics and other sensors, they are able to have a synoptic view to capture from the ground. Then it could be even satellites in the LEO, or it could be satellites in the GEO. For example, we have got remote sensing satellites working in the GEO as well. The Indian satellites of INSAT 3A, 3DR, etc. They are weather monitoring satellites. What they sense from space, 36,000 up in the geosynchronous orbit, is the cloud pattern, the cloud movements, and other upper atmosphere activities. So geosynchronous orbital platforms could be either GEO or LEO. Then we can have suborbital, that is a domain which is about 100 to 200, 300 kilometers. We can have some sort of balloons or something flying there. We could have drones. Then this is suborbital platform, is something essentially around 100 kilometers or so from the surface of the Earth. So these various types of platforms could have sensors on board and fly, including balloons actually. And the most important element that I wanted to focus here is that the instantaneous field of view, what we call, how much the sensor from whatever height it is operating is able to see, and how much it can capture. So this is that whatever angular means subtended angle, when it translates to the surface of the Earth, how much area, diameter of the ground projected instantaneous field of view, that is generally sometimes we call what the swath of the onboard sensor, how much it is able to see instantaneously. And mind you, we should always remember that these bodies are moving in space. and they have to move there with a lot of compliances to the orbital dynamics. So they are moving at very fast rates. So you will be surprised to know that the geosynchronous communication satellites or the remote sensing satellite at the geosynchronous altitude of 36,000 kilometers, it is flying at an instantaneous speed of almost 3.3 kilometers per second. You can imagine that. So this is basically at that altitude, the 3.3 kilometer per second is required to overcome the gravitational pull of Mother Earth and to stay there safe and continue to move around. Why I am talking about this speed, etc., is you should have a feel of how much the sensor has to be stable at these altitudes when a platform is moving such a huge speeds, and how much of information about those stability and other aspects at the ground when the data comes, you will have to think about to do the correction factors, ortho rectification, radiometric corrections, etc., I think most of you may be familiar with those terms. Otherwise, you will definitely learn it. And coming down to the LEO orbital reference height of about 500 to anything going up to 800 or 1000 kilometers, then the platforms are moving at almost 9 kilometers per second. Of course, coming down to the suborbital and all, definitely the speeds are going to be more. Otherwise, and of course, these are all powered flights, so there is no issue. You can manage it and come down. Yes. Now let us quickly go to the sensor classifications of what is a passive sensor or an active sensor. Here again, there are two types of sensors at the top level. One is the sensors, electro-optic sensors, where you are basically dependent on the solar energy and the illumination of the solar energy on the object of interest, the reflections, the absorptions, the incident radiation, the reflected radiation, the thermal emission, etc., emanating out of it because of sun's activity. Essentially, as we all know, we see an object because of the light falling in it on and reflecting back and it coming and falling onto our retina, and then we are able to sense that something is there, and it is part of our internal processing system that we are able to understand what is the object, what is the color, what are the features, etc., Similar thing is transformed in an electronic or electrical domain in remote sensing. Sun is illuminating the body somewhere here. Suppose we wanted to have an object here, is illuminating the body, it is reflecting, and this reflected energy is being sensed by the sensor. It could be a spaceborne sensor, airborne sensor, or any type, or a balloon, or a rotary aircraft, or even it could be a ground-based sensor. The only thing is that remote sensing means that it should not be physically connected. You cannot connect a sensor and wire it onto to your target body. It is that. And subsequently, we have this backend connectivity of the incoming data. So data processing, then various modes of augmenting the data, correcting rectification of the speeds, etc. that I said. Then interpretation. Finally, it goes out as a product. This is the general schema of things that happens in the remote sensing, data sensing to data product generation. So let us look at how a satellite sensor works there. So if we're talking about, this is typically we are trying to talk about remote sensing from the low Earth orbiting domain, where satellites generally fly anywhere around 500 to 800 kilometers. This height of 500 to 800 kilometers is basically designed by what mission we are going to operate. Is it going to be a surveillance mission where you wanted to see an object with very clarity, or it is going to be some sort of vegetation monitoring that you are going to, somebody wanted to have a look at what sort of illegal cultivation is happening in one part of the country. So the mission decides what sort of sensors we are going to fly. But orbital dynamics are going to be the same despite what are the mission you are flying. Because Earth's movement, the satellite movements, the altitude that going to operate, everything will decide at what speed you are operating and what is the orbital duration. Typically, a remote sensing satellite has an orbital period of about 90 minutes or so. That means it completes one revolution around the Earth in 90 minutes. Every 90 minutes, it completes one revolution. So you can imagine that a circle or a circular orbit defined almost 300 plus 6,000 kilometers, 6,400 and odd kilometers of the Earth's radius. You add together and define a circle in outer space with the center of the Earth as the focal point. Then you get that orbit. So they move around, and you have got onboard sensors. These are the sensors, and this is what we call the way it is. When the satellite is moving, Earth is below, and you can look down. You can have your sensors on board, collect the data of the area of interest, and then move on. And this path is called the orbital path, and the width of this arrow is called the swath. And we have got sensors on board, and they will look at whether if it is an electro-optical sensor on board, the sun illumination angle is very important. At what time of the day you are flying is important. And another point that you can see from this diagram is that, see, from one orbit to another orbit, even the first orbit, second orbit, there is a shift you can see. This is because as you are flying in space, one orbit of 90 minutes, the Earth has already rotated below you. Actually, the satellite is moving, satellite's orbit is fixed in space with respect to the center of the Earth. But Earth is moving 24 hours, no, it is completing one rotation around its own axis. So this tells that if one satellite is up in space, we have an opportunity of looking at the entire globe. That is means every 90 degrees movement, you are going to see a new domain below, because Earth has shifted. So there's a little bit of arithmetics that you all can do. You work out and see that what is the time taken. 24 hours, Earth is completing one revolution. Then you can say the surface area calculations and see how much ground it is going to cover. Some numbers I have provided here. This is taken out of some standard, this one. So it will scan. Then it will, satellite is moving. This is the swath, and what data is being accumulated on board. And what happens is this data is accumulated on board, and whenever you have a visibility of one friendly Earth station down below you, that means suppose you are moving over India here, and before you come over India, you would have moved over China if you're coming like this. And most of the satellites are coming like this, because as you can see, they are all in the polar orbit, north-south. Communication satellites are in the geosynchronous orbit. It is in this domain that communication satellites are there, whereas remote sensing are in this domain, that is North Pole, South Pole domain actually. So as they move in from north to south, so as move in, they could have sensed these much areas of our interest. So once they come over India, and when you have a friendly ground station below you, what you do is all this data that is accumulated on board through your memory mechanisms there, huge memory arrays are available on board with this new generation technologies, no, and miniaturization, a lot of possibilities are, the terabytes of information can be stored. They gets downloaded to this Earth station, and the onboard memory is then free. Then you start going ahead and start taking data about this part of the country, plus below if Sri Lanka is or any other country is there, continue. So this is it. So here you can see that 90 minutes of duration in space gives you one full revolution. And if you want to revisit the same place again and again, that means you will have to have continuous array of satellites coming one after another here. So then only you will be able to revisit every now and then. In the theoretical or the hypothetical case of one satellite alone having this, then what we have found out is that the possibility of a revisit to an area of interest happens once in 22 days. So that is what here, repetitivity cycle here. So quickly, I for lack of time. So we are talking about sensors. Now we are talking about active and passive sensors. So active means, one moment, I have noted down here. Oh, passive sensors. So passive remote sensors. Sensors which sense natural radiations either emitted or reflected from the Earth. Sun as a source of energy radiation. So radiations that are by nature available from sun, you reflect it and then you pass it out as some sort of body feature. They are being sensed by the active sensors. By the passive sensors. Active sensors are, you have transmitted some energy, you have some external energy with you, and you transmit and illuminate that energy onto the object of interest, get the reflected energy back at you, and then you try to assimilate and try to find out what is happening. So Sensors which carry electromagnetic radiation of a specific wavelength or band of wavelengths to illuminate the Earth's surface are called active sensors. Sensors which sense natural radiations, either emitted or reflected from the Earth, are called passive sensors. So this is the broad classification of the active and passive sensors. You can here say, you can see one thermal image. This is a passive sensor. This is advanced, very high resolution radiometer is one payload that we have flown in one of our satellites. Of course, this image does not belong to that satellite. So essentially that payload has picked up the thermal imageries from emanating from the ground. It could be the thermal imagery of the cloud formation, or it could be anything. Only the analyst will know because data goes to them. And this is the active sensor, which is a radar, CubeSat scatterometer radar image, where you are pumping some data from the radar and it is illuminating the body of interest, which is to be sensed, and that body will reflect it back, and something in terms of radar cross-sectional area is detected and interpreted by the sensors. We will now come to some system characterization. Why I'm explaining these things, because these were the parameters when I got into this remote sensing domain of conceiving systems for the end user. These were the parameters where we were not aware of. We were only talking about systems on board, electrical systems, electronic systems, etc. But the rudimentary things, what is the spatial, temporal, and spectral and radiometric resolutions that we need to understand and implement in the system, that is very important. That is why I'm trying to highlight those things here. Shilpa, just tell me if time runs out, okay?
Yeah, sure.
Yeah. We are on the same page so far?
Yes. Remote sensing system characterization.
Yeah. So we will be now talking about the spatial, temporal, spectral, and radiometric resolutions, which are the basic 4 characteristics of whatever may be the sensor, any sensor, whether active or passive. We will have to work around these 4 types of resolutions: spatial, temporal, spectral, and radiometric resolution. I have tried to capture those in the forthcoming slides. So this is a spatial resolution. So explaining on this, spatial resolution specifies the pixel size of satellite imaging covering the Earth's surface. What is the smallest size of the area of an object? It can be Earth, or it can be a tree, or it can be any other body. What is the smallest pixel size? It is just like our television screens, no? The more pixels you integrate in a given area, you have got a better clarity, because you have got more and more sensors embedded in a small area. So what is the dimension, the pixel size? So you can see the characterization here. It is a capability of the sensor to discriminate the smallest object on the ground of different sizes. And it is usually specified in terms of the linear dimensions, the 30 meter, 5 meter. The 5 meter resolution means you can see there are 2 objects kept side by side. Okay, 5 meter by 5 meter. So probably a 5 meter resolution sensor, electro-optical sensor, or any other sensor for that matter, flying in space around 300, 500, or 800 kilometers, if that is qualified for this sort of activities, he will be able to differentiate between these 2 objects. A small object, 5 meter by 5 meter lying here, and another 5 object lying here. They will be able to differentiate as 2 distinct objects. That is what we call pixel resolution. So this is 5 meter resolution, 1 meter resolution. So then output display you can see. Okay. So this is more precise. Okay, 1 meter is you get more and more output. That means the reconstruction of the image will be on a much better plane. Now you are coming to spectral resolution. So spatial resolution will essentially tell you what is the pixel size, what is the minimal detectable threshold in terms of the size of the object or phenomena that you are going to sense from space. The second one is the spectral resolution. So as we all know, the electromagnetic radiations or electromagnetic spectrum is that one that enables us to communicate with each other or detect. And every body in this universe, whether it is a metallic body, or it's a human, or a small animal, or even a blade of grass, everything has got its own characteristics of radiation. It is radiating. Now, we are not able to see those radiations, or we are not able to perceive those radiations because we are not equipped with those phenomena, and whatever we see are in the optical range of our own sight, decided by what we are capable of and what is the bandwidth of our sensors, that are the eyes only. But here you have the visible spectrum, you have got the infrared spectrum mostly, and there is a microwave spectrum here. So the entire and long wave radios and other things, no, the satellite communication, everything comes in this FM, AM radios, and all other microwave will come on this side. So here, this is the domain where we are going to have the remote sensing. So which spectrum is being utilized? That means each spectrum will have got its own characteristics, and how many number of bands are being used. So the spectral resolution specifies the number of spectral bands or bandwidths in which the sensor can collect reflected or emitted radiance. Then the number of bands alone is of no significance. The position of the band in the electromagnetic spectrum is important, because each of these frequency, these units, no, or these bands will have their own characteristics. Some will be beneficial for some sort of remote sensing, some will not be beneficial for that, and some other hyperspectral or multispectral or some microwave region may be good for some specific activity. So the purpose or the mission decides which band of operations and what type of sensors you are going to deploy. And general definition is that if you are talking about a high spectral resolution of sensing, then they say that about 220 bands of these narrow bands of frequencies, no, each, no, they will be utilized. So that means it's a broader band of frequencies are being sensed. That means the voluminous data is going to come out. Medium spectral resolution, if you have a 3 to 15 bands of sensing capability on board, then you got medium resolution. Low spectral resolution, only 3 bands. Okay, sometimes no, only very small 3 bands of sensors are available. But these are the basic definitions of spectral resolution. But as we have grown, we have now come to a stage where see, more and more spectrum and more bands of frequencies are being utilized, and the sensors are becoming more and more available. So that is the status today. The most important criterion for the location of spectral bands is that they should be in the atmospheric window and away from the absorption bands of atmospheric constituents. That is because, see, already the emissions that is happening on the bodies are of very low amplitudes. So the sensors which are flying at 600, 700 or 800 kilometers, they should have the sensitivities to detect and take in these radiations, and then without much of attenuation. So if you are not working in the proper bands where the upper atmosphere impediments are going to eat away into your already feeble emissions, then you are done. So what you will have to do is select a band where inherently that the impact of the upper atmosphere and other activities happening there towards degrading the signal as they flows towards the sensor is avoided. This is the basic thing I'm trying to say. Now the third one comes to okay, this is some capturing some spectral response differences. This is the thematic mapping band for near infrared area. You can see the distinct difference between what is the product output. Now you can see the features are more distinct here. This is becoming more sharper. This area has become more clear, etc., etc. So actually, this is the domain where the ground-based processing will come into play, because you get the raw data, you do the ortho and radiometric corrections with whatever algorithms you have, plus you you will have to apply your own additional processing techniques to bring out each and every aspect of the image. So this thematic mapping band 3, this is having some sort of characteristics showing. Here you can see this particular area is and it again what I'm trying to again and again say is, probably you are interested more in this area, not other features. So probably you did the sensors for this particular activity. Okay. Whereas you could, if you are more interested in highlighting this area, probably you could have gone for another band of operations. I hope you understand. Now, spectral resolution, one more case. See, this is a nice young girl sitting here. She has got very colorful attitude, but in a black and white sensor, if you are employing for looking at her from space, no, probably she would look like this. It's a single sensing device, black and white, and that frequency bands are limited. So the imagery that will come out after processing will show her this. In fact, the real she is this. So if you want to look at her in the real sense of what she was and what she is, now you'll have to employ a 3 wavelength combined RGB sort of sensor. You're going to have need 3 sensing devices, red, green, and blue. So that will give you the real picture. So you have now talked about spatial resolution regarding the pixel, how much is the smallest size that can be differentiated by the sensor. Then you are talking about spectral resolution. Now we will go over to the next type, which is the temporal resolution. See, temporal resolution basically specifies the revisit frequency of a sensor for a specific location. How frequently you are able to see. So earlier in one of the slides, when we were talking about the sensor in the space, about one single satellite scenario, I said that with one satellite flying around 600 or 300, 400 kilometers up with a orbital period of about 90 minutes or so. So it will see one specific area in that flight. Next flight, by the time it comes back into the same domain, Earth would have shifted. So, but if our intention was, so suppose what is happening at Manipal, I have a satellite up in space and I have programmed it to come to Manipal and it has seen. Now it has gone, and next time again it revisits Manipal would be 90 minutes later. By that time, Earth has moved. So satellite up in space is in a common point and you have already moved. So if you want to if you want to detect what is happening at the Manipal, where you are all sitting and trying to do some activity there, if I want to see again and again with a repetition rate of at least 1 hour, that means I should have satellite coming in after the first one has gone. So time series. So if you look at the target latitude of going up, if you are going up from the equator is 0 and you are going the positive north towards 90 degrees, you can see that this is the time of average revisit times. Okay, you can see, you can differentiate here. So as the latitude increases, okay, as the latitude increases here, the revisit is 1, 2, 3, 4, 7 or 8, you can have it. But if it comes towards this polar structure, every satellite is converging here because it is in the north-south axis. So what I mean to say is, a satellite is here and it is sensing something. And if you have a ground station here in the polar area, every satellite will be seen here. Whereas if you have something in here, so you should have many more satellites here if you want to have a frequent revisit of this particular latitude. Then you should have more number of satellites. And if you wanted to have a look, means Earth station here, you will have visibility all the time. But this is of no consequence to us because most of the habited areas are in this domain actually. Now we are coming to radiometric resolution. So radiometric resolution is basically, it specifies the capability of the sensor to discriminate two targets based on its reflectance emittance difference. That means, see how much, now you talked about the spatial element and how much size will decide the sensor characteristics. Then we talked about the frequency responses, what frequency of band of operations the sensor is working and what will be the impact of that selection criteria on the sensor output. Then we talked about temporal resolution, which says if you want to have a constant sensing of one particular area with you wanted to bring in some sort of change detection, what we need to do. And here the fourth one is how sensitive the sensor is to subtle change in the radiance or the reflectance characteristics of the body. Okay, so here we can see you have a image that has come out of your system with a sensor at the 8-bit 256 gray shades. Here is 4-bit 16 gray shades. So you can see that with the increasing number of sampling, you are getting a better and better and more resolved and more sharp features actually. So the sensor, if it is having a better sensitivity, that even for a slight subtle change in very feeble change in the emissivity or reflectance of the particular target can be detected, then it transforms into or translates into better sensor performance. So these are the basic things that I wanted to say regarding the basic resolution characteristic of the remote sensing. So now, having given you some sort of brief introduction to the rudimentary remote sensing characteristics in terms of sensors and other thing, now we will come to the topic of the day, that is the space-based remote sensing, the Indian perspective. So coming to that, so as an introduction, I would like to say that see, the Indian space program is application driven, and we have made over the last 4 decades, we have a very vibrant remote sensing program, and we have deployed and operationalized a variety of space-based and airborne remote sensing sensor systems for various science and technology applications. Actually, we started from scratch with nobody to hold hands, and only thing we had some exposure to some of the sensors and other technology developments happening with some friendly countries and all, but they were not also very forthcoming, because space is a very highly competitive domain and nobody was ready to help. So we had to develop indigenous technology by our own modes. And we started in a very modest way with the experiment on detection of a coconut root wilt disease. That means somebody had a problem with coconut root wilt disease, and they were all struggling to find the reason for that. Then somebody suggested that we could go by the remote sensing mode, and that is a time when we flew some sensor on board a helicopter and started. That was way back in 1970 when we started this program, and it has definitely evolved over the years, and today we are self-reliant in every aspect of technology and applications, with a homegrown and end-to-end capability spanning the entire space segment, ground segment, and the applications program, with particular emphasis on capacity building. We have also built institutions who would train the people in the art of or the science of remote sensing. For example, we have set up that Indian Institute of Remote Sensing, Dehradun also, where they have ongoing and running programs to train those people who are interested to come in. We had flown a series of Earth observation systems, starting from the Bhaskara satellite, the first experimental Earth observation satellites. It was in the year 1979. And now we have graduated and come to the Cartosat 2 series right now. So you can see this is this is a very typical representation of what we have achieved. Right now, from the last the inputs that I got from the ISRO website, we have got 18 Earth observation satellites currently in orbit, one of the largest constellation of remote sensing satellites in the entire globe, dedicated to primarily for civilian applications. So we have what is very important. You can see that we started off with a spatial resolution of 1 kilometer long back in time, but today we are come and we have graduated. This shows 0.8 meter, but I can tell you in confidence that we are hovering around 0.25 meters or 25 centimeters. That means today we have capability to sense objects that are as small as 25 centimeters. So you can imagine what it translates to, and you can see that imageries that we have seen. That entire gamut of remote sensing capabilities are there. You can see the cloud formation, Himalayas, then you can see the ground terrain, then water bodies, the buildings and infrastructure, stadium, etc., etc. That means here you can see 1 kilometer what we were seeing, and as we progressed, how we could differentiate between the features of the individual the ground bodies that we were sensing. And here, look here, 0.3 meter we are here. And a whole series of satellites are built, from the land and water theme to high resolution imagery theme to ocean and oceanography to weather and climate. So we have got the array of satellites across the entire gamut of whatever we need to observe. National capabilities. So Cartosat 2, 2A, 2B, 2C, these were the satellite which we were planning. That I was in the beginning stage. I said that we were conceiving and planning. This is the radar imaging satellite essentially, because electro-optical satellites or the sensors, as I said, the passive sensors, they are based on the sun illumination angle. And if you want to see what is happening in a specific area, and if you want to have a change detection, even if you have a series of satellites coming to the same location one after another, if the sun illumination conditions are not consistent, so then it's not going to make any sense. That means wherever in Manipal, today at 9:30, what is happening? Tomorrow also, same 9:30, you should be able to sense. That means you are assuming that the sunlit conditions or the radiance conditions or the reflective conditions of the sensors sitting up out there are same as the previous sensing. This is what we mean. And if there is a subtle change in the local illumination conditions, then that you know very well as an analyst. And once the data comes in, you can just try to manipulate and then try to bring in that changes as well. So, but sometimes you need what is to see what is happening in the night as well. Then what do? Where is sun in the night? Sun is gone. So that is the place where the remote sensing, active sensors like radar sensing will come. Radar will see through the atmosphere and through day and night. And another aspect that we'll have to think at this stage is you see even this sun radiations and other emissions, they will be deflected and eaten away by the atmosphere as well. And sometimes during the monsoon season, clouds are so high that via the sensors, electro-optical sensors, are not able to see anything. What they see is a hazy picture of what is below it. So that point of time, for our national security or other specific applications, we bring in the radar-based or active-based sensors. This is a radar sat, where it looks at the ground, pumps a huge amount of RF energy, that bodies get illuminated and they reflect back using their own characteristics of reflections, and it is captured back by the onboard antenna systems, and the data comes back to the ground processing units. Then we have this ocean regarding, especially with sensors customized for the observing the ocean color monitors, SCATSAT, ROSA payloads, etc., etc. And then I briefly talked about the weather and climate monitoring. These are the INSAT 3A and the Kalpana satellite, you might have heard, because named after Kalpana Chawla. The BHR, very high resolution radiometer. These are the satellites which are orbiting in the geosynchronous orbit of 36,000 kilometers altitude. So instead of a series of satellites at low Earth orbiting satellites constrained by their own limitation of the sensors on board, these satellites, single satellite, because they are in geosynchronous orbit, they are able to see by the dynamics of orbit at least 1/3 of the globe. The 17 degrees subtended angle is there from 36,000 kilometers. You can see, you can also imagine that if you draw a circle with that sort of thing, you will have 1/3 of the globe covered from that altitude. So if you position them at the right position in space in terms of longitudinal orbital slots, then you will get the area of interest with respect to our country. So these are it. So this is the growth of Indian remote sensing. Now, what are the applications? So briefly, we can look at that. So water resource monitoring, disaster management, disaster detection plus mitigation, defense and security, agriculture of means soil, type of soil, what type of this one, then forestry, regarding the growth or somebody is destroying these geosciences regarding the mineral wealth and other activities regarding the ocean. And a little bit elaboration I have brought in here, space applications in diverse areas. So area and production estimate, because this is all of economic interest to the predictions, in season multiple forecast, satellite data plus agro meteorology, market economics, because how much of what is the acreage of paddy, what is the acreage of wheat, what type of other this one other, whether is there any damage done to the crops because of some sort of disease or some sort of infest attack, etc., etc. Then drinking water, groundwater prospecting zones and recharge sites, So what we have seen is that if you based on remote sensing data and go for water exploration, 90 to 95% of success rate has happened using bore wells, increased water levels. If something is happening in a specific area, then that area can be given as a, and mind you, these colors and everything, it is all generated on ground. Satellite does not see this in terms of color or like this. This is where I think geoinformatics and your geosciences and your data processing techniques and skills will come out. This is the domain where your chapter members should focus. The raw data will come from the satellite, and then you will have to work around those data with your fundamental and foundational knowledge of other matters. So watershed development, even is a very nice way of saying things. Actually, potential fisheries. Hello. All right, right, done. Okay. So space application in diverse areas. Again, assessment of forests. These are all little bit of expansion of what I said earlier. And disaster management, near real-time information regarding flood and inundation, cyclone track. See, once there is raining or some landslip or something happening anywhere across the country, nobody is able to go. When there is a catastrophe hits, you are not able to go there. So I am very proud to say that the remote sensing, space-based remote sensing was the only means, and the space-based communication was the only means when there was the tsunami in the Andaman Nicobar and all. We could have connectivity and the real sense of the activity by programming our satellites to pass by that domain again and again at some cost to the orbital life, of course. So we could do that. Then another thing is tele-education. Of course, this is coming under not remote sensing, that's the communication domain. Snow and glacier studies. That's a very important activity that's happening under the remote sensing. National urban information systems, including the land utilization and how crowding and all those things, illegal occupation of government land, etc. So that's what. And of course, this is what I wanted to see, the real pictures of application level, how the pre-event and post-event. This is change detection. Uttarakhand flash flood disaster. The flood happened, and because satellites are regularly going around and collecting data, and we have got a database, we could know how it was like this. There was something like this. Post-event, you can see. See, it's the same thing. So this is an electro-optical payload, same sun illumination conditions. When the satellite revisited the domain, earlier it was like this, now it is like this. So post-event. So this gives us a great handle on looking at, and here it is, you can see the Idukki Dam area, water catchment area, the Erimala zone where the Naval Academy is there, so some buildings are seen. Bepur River, that is in Kerala, Palgad area, it is mostly what you call barren area like that. Kochi, you can see that basic outlines of the port, etc. And this is again the thermal mapping of the ground trace of Kerala as a whole. Of course, and this is Hirakud Reservoir capacity estimation. When the case of water dispute between states, like interstate rivalries and all, no? So remote sensing can be brought in to have a look at the water estimation. So with imageries, change detection, or somebody will say that I don't have water. Somebody can say that with remote sensing that yes, water is there. You are only not able to get it. And there is a portal that has been generated by the National Remote Sensing Center of ISRO. This is basically because I said earlier, terabytes of data, voluminous data from so many years, 1970 to as of now, new generation satellites are giving you voluminous data second by second. These are all lying in the archives. And they have developed a Bhuvan portal, and now you can access that Bhuvan portal and try to get some data. Because of earlier data policy that the data which was less than 5-meter resolution was not being given, but now I understand that limitation also is going away, and shortly you will get it. Now planned Indian high resolution satellite, I will pass this because this is a new generation satellites which will give you the only thing you understand that they are going to give you a 25-centimeter resolution. That means our mobile phones, two mobile phones kept side by side can be picked up from space at 800 kilometers, and you can definitely say that two mobile phones are there in this room, of course. And this is an international scenario where high resolution sensors are there. For lack of time, I will run through it. And of course, this is that electro-optical sensors of ISRO, where we have grown. You see, 1985 started off, and the spatial resolution was in meters, was that time 10 kilometers we started. Now we are almost like 10 centimeters we are coming here. and the swath has also increased. The instantaneous field of view and 10 meters, now we are able to see from space about 3,000 kilometers at one stretch. So the complexity of the sensors as well as capabilities have gone up by leaps and bounds. Actually, this is what I'm trying to capture here. Now this is the 3-tier imaging by ResourceSat 2A, advanced wide field sensor, 50-meter resolution. This is linear integrated self-scanning mode of camera system. There are electro-optical systems, and how one by one. See, actually what is happening is the image production and the output does not come from these imageries alone. You have already data with cartography, conventional cartography, and other sensing methods. And what essentially you are doing it, you are trying to supplement those data with respect to along with that remote sensing data, or vice versa, so that you get the real picture. And okay, this is the weather monitoring imager inside 3DR. I have seen that some, and this is oceanography for us. These are all sensors that is developed by indigenously by India, because nobody was able to give us the technology. So this is why I wanted to capture and tell you what is the current state of affairs in ISRO. So look at this. This is the weather maps, cloud formations and all. This is the VHRR imagery we captured from 36,000 kilometers, and their onboard sensors are there. They are doing remote sensing here actually, because they are looking at the cloud movements and all. And onboard camera systems are so programmed and so capable that every half an hour you can take a picture. This is the entire globe picture. Of course. So you can see. So next half an hour, from now, when the satellite is flying, probably this cloud would have moved towards this mainland or moved away. So with this time series analysis only, you are able to tell from where direction this one coming. The clouds are moving, and whether monsoon is likely to hit us or not. Look at this data. This is one of our the first day imagery of one of our top class satellites actually. So I am very proud to say that I was associated with conceiving. This is meant for some sort of national security application. So once the first flight happened and it was flying over Dubai, this is a picture transmitted by the satellites, uncorrected, very, very raw imagery. You can see that you are able to capture the size of the objects. Even cars are going on the highways are visible, and you can see the building. And trained analyst, if you are giving this data, you will be able to tell what is the height, what is the time, what is this one, what building it is, etc., etc. So this is it. So this same sort of imagery is raw data. When you do the ground corrections and doing the processing part, it will bring out the features of this one, high resolution imagery, same Cartosat 2 series. So these satellites are having a electro-optical capability of about 25 centimeters or 30 centimeters. So this is the capability we have today. Now, I talked about the active sensors, radar imaging satellite. This is the first SAR satellite we have built. So these are all different imageries captured by that. And this is an L-band synthetic aperture radar imaging. As we said, in the case of the radar imaging satellites, the spectral means the responses and the spectral resolution is the most important criteria, because if you are, it all depends on what mission you are at. Actually, if you wanted to look at some foliage or some vegetation, this one, the lower frequencies only will work, higher frequencies will not work. So one L band, that is 2000 megahertz bandwidth, means the operational band of frequencies. No, this is one synthetic aperture radar that we have developed at Space Applications Center, Ahmedabad. This is a state-of-the-art feature. You are able to talk about vegetation and all. This outputs and data will be used for the Northeast. Now we are also proud to say that we are in jointly we are trying to develop a NASA ISRO synthetic aperture radar, which will give you a 5 to 10 meter resolution over a 225 kilometers swath. So we are building the satellite with some technology available from NASA. It is already making news, and it is going to be launched soon. So it will give you a capability of observing in the S-band. S-band in the sense, metallic objects and other things will be picked up from space, and it will definitely try to help us in this one. And now emerging technology, geographical information systems, you are all new generation kids, you will be knowing what it is, but essentially to capture where we are with respect to GIS is. So it is an integral thing now, integrated, coordinated, cooperative, collaborative, and it can support projects, systems, networks, or societal things, So this is the way it has emerged and evolved. It is means a culmination of so many activities, giving a 1 plus 1 is not 2, 1 plus 1 happens to be some 3 or 4. So GIS integrates disciplines. GIS integrates disciplines and technologies such as remote sensing, surveying, photogrammetry, spatial analysis, cartography, computer science, etc., etc. These are the areas where you have opportunity. Data comes, raw data comes and gets archived, and it is for you to get the data and develop your own skills and algorithms and other technologies, and try to extract as many data outputs and as many information as possible. This is the challenge. So levels of this one, no? So multiple level 1, level 2, level 3, like that, no? Database access. Here also again multi-layered customers, streets, parcels of land, then land usage, uh, real what you call water level or whatever it is, real world rather, sorry, I'm not able to read. So these are the way GIS will enable you the multi-layered, and that means feature rich. Actually the imageries are, the data is feature rich, but unless you have the capability or the algorithms or the technology to analyze the data and to bring out all those various details, then that's not no consequence. That is where GIS comes in. Layering of GIS. So this regarding some sea imaging. Okay, sea floor topography is available, then backscatter is there, sediment thickness is available, geological map of the sea floor, all are integrated into one image, and you can by this one design or default, you can take out area of interest for you depending on what is your area of interest. So remote sensing data applications, we are coming close. Energy, land cover, etc., etc. You know everything. So every domain of modern life, 21st century life, is enabled by satellite systems, especially remote sensing. Especially the economic growth of the country, remote sensing is contributing and collaborating in a big way. So pursue answers about global climate change. Some of these imageries, no, this is the real imageries of NASA. Some of the satellites, high technology satellites, weather monitoring, glacier formation, or all those things. No, how the glacier is melting and the impact on ecology, etc., can be studied. Plan for hurricanes and other tropical storms. So it gives you advanced information that the hurricane is coming. Actually, if you look at the history of remote sensing and the applications, no, we can see that thousands of lives and have been saved because we had advanced warnings regarding the hurricanes coming to the coastal belt of especially in India, Orissa, and other places. Many people have been evacuated, and that way we could save much life. And of course many people who are going to see, and they can be also warned in advance, etc. So it enables a lot of societal application as well. So enjoy informative and visually appealing weather forecasts. This is a real means formation of the cloud, and etc., etc. Of course they're all ground based processing and output of the systems going in. No, this is what I got from the Worldview 3 satellite image of the day. That was yesterday. I was scanning and got this. Actually see how this is Maxar. Maxar is the agency who is running the satellite. He may not be running the satellites. He may be sourcing the data from some of these high-end satellites, and he may be doing his own analytics and his engines, no, to run his own customized algorithms and to take out. It all depends on which domain of the this one, no, industry you are servicing actually. So this is it. So finally, to conclude, a picture is worth 1,000 words. Satellites provide consistent, routine, global coverage of environmental events, and seeing is believing. So our satellites and our assets in space is helping us in our economic endeavors and growth forward. And it's a challenging and complex task. Building space systems alone won't work. We'll have to have the ground infrastructure and the ground capabilities and the technological drive and acumen to get the data, process it, and get outputs which will be beneficial for the humanity at large. And I hope our chapter that got inaugurated today will take these words into consideration and work judiciously towards that objective. So to conclude, so this is what I always want to say. We are not where we want to be. We are not where we are going to be, but we are certainly not where we were yesterday. Said by Martin Luther King, January 1968. This as well applies today to any technology, especially with space technology. We have ambitions, aspirations, and definitely we are yet to make much more progress. But rest assured that we are on the march, and we will definitely reach there. Thank you.
Thank you, sir, for the
Thank you.
very informative and inspiring talk on space-based remote sensing from an Indian perspective. I'm sure that the UG and PG students have deeply benefited from the talk. This will surely inspire our students to work towards the same. Sir, I request you if you could unshare your screen, then we can share our screen in that case.
One moment. How do I do that?
Icon beside the mic. You can click on icon right
Beside
side.
the mic.
Right
Next
side
one,
of
next
the
one.
mic. Right side of the mic. The cross one.
Okay, thank you. Thanks.
Thank you, sir. On behalf of IEEE GRSS Student Branch Chapter, MIT Manipal, and Department of Mechatronics, we would like to present you a virtual memento as a token of our gratitude and love. Thank you so much, sir.
Yeah, I accept it virtually. Thank you very much.
Thank you, sir.
Thank you, sir. I would now invite Dr. Pallavi Mane, Branch Counselor IEEE SBM and Vice Chair IEEE Mangalore Subsection, to give us a brief overview of the IEEE activities being carried out at MIT. Ma'am, over to you.
Can I have a sharing access?
Yeah, sure, ma'am. Sure.
Yes, ma'am.
We can.
Now you can share your screen, ma'am.
Is it visible?
Yes, ma'am.
Thank you, sir, for briefing us and giving an insight on the chapter and the activities that have been carried out with the design, the applications of remote sensing. Thank you very much. On behalf of MIT Manipal, I welcome to join IEEE student branch as students, graduates, and professional members. At MIT Manipal, we have several chapters: CAS, RAS, ComSoc, Computer Society, EMBS, Signal Processing, and so on. We have affinity groups also, Women in Engineering and SITE. So I welcome students to join IEEE, get connected with the people, the resource people, the researchers, the academicians, not only in MIT Manipal with interdisciplinary or interdepartment faculty members, but also you can contact the neighboring colleges. We have IEEE Mangalore subsection, under which we have 14 student branches of various 14 engineering colleges. You can collaborate with them. You can work under academicians who are working in different colleges. Not only at this Mangalore subsection level, but you can also volunteer at Bangalore section level. So there are various activities that are being carried out at different levels, at the institute level, at the society level, at a Mangalore subsection level, as well as Bangalore section level. So with these few words, I request you to join IEEE student branch as well as professional members. And if you have any difficulty in joining, please contact me. We as a team of IEEE student branch are always ready to help for you. At the same time, I would also like to thank Dr. Shilpa and Dr. Shamlal, who were instrumental in initiating the process of starting this IEEE GRSS at MIT Manipal. Thank you very much, and welcome to the family of IEEE.
Thank you, ma'am. With this, we have come to an end of the inaugural function. And now I request Dr. Shilpa Suresh, Faculty Advisor, IEEE GRSS Student Chapter, IEEE SBM, to deliver the vote of thanks. Ma'am, over to you.
Thank you, Jennifer. Good evening, one and all. It was indeed a very great evening. On behalf of IEEE GRSS Society, Student Branch Chapter, MIT Manipal, and Department of Mechatronics, I extend my sincere gratitude and thanks to our Chief Guest of the Day, Mr. Jayaram Kolangara, for sparing his time for inaugurating the IEEE GRSS chapter and for delivering an insightful talk. Thank you so much, sir. Next, I would like to thank Dr. Commander Anil Rana, Director of MIT Manipal, for all his support for the conduct of the program. Thank you so much, sir. My hearty thanks to Dr. Jaya Sreevalsan Nair, Chair, IEEE GRSS Bangalore Section, for accepting our invitation to grace the occasion with her presence. Thank you, ma'am. Now let me thank Dr. D.V. Kamath, HOD, Department of Mechatronics, for his encouragement and support for organizing this event. Thank you so much, sir. I would like to extend my warmest gratitude to our Students Branch Counselor, Dr. Pallavi Mani, for her support, suggestions, and constant encouragement. Thank you, ma'am. I would also like to thank all the EXICO members for their wholehearted efforts and support in the preparation and conduction of this event. Thank you all. Last but not the least, I thank all the faculty and students for their participation and cooperation for the conduction of this event. Thanking you all once again.
Once again, thank you all for your cooperation and for making this event successful. Have a great weekend. Thank you.
Thank you, and all the best for all the events that, looking forward for a very active participations from all students and faculty members. Thank you very much.
Thank you so much, sir.